Okay, I'm going to introduce you to one of my favorite derivations. Now, I know that's kind of geeky to have a favorite derivation, but I do. I have a favorite equation, I have a favorite derivation, and I'm proud of it. Okay, so we are going to derive current. All right, what is current? Now, to think about it, we think about, let's have a wire here that's going along, and I'm going to put kind of a pretend boundary around that's cutting through that wire, and that wire continues on. And my question is, how much charge, Q, flows across that boundary in some amount of time? Okay, so if I think about this piece of wire having a length, I'm going to put a dx. It's a small length of dx. How much of that charge flows across that in some amount dt? Okay, so we define current as being dq over dt. How much charge flows past a point in how much time, in some amount of time. So our goal is to use this picture here to figure out what that is in terms of some fundamental parameters. Okay? So this video you're going to want to watch twice. It's going to cover material for the first reading in chapter 27 as well as the second reading in chapter 27. But I want it all here together. Okay, so to start, we need to first figure out, okay, well, how much charge is in this section of length dx. We're going to assume this much volume of charge moves past that point in this time interval we're interested in. Okay, so how much is there? All right, well, let's say there are n electrons, and they each have a charge E. So the total charge is the number of electrons times the charge of an electron. So that would be the total coulombs, and that's going to go in dt. All right, well, the number, we'd have to count that, but generally we probably, more so think how many electrons per unit volume there are. And we call that a number density. And that's given by an N sub E. So this material, whether it's copper or aluminum, it has a certain number of electrons, conduction electrons, per unit volume. And we call that the number density. Okay, so if that's the case, then N is going to be the number density times the volume of this section. Okay, then we multiply it by the charge, just as we had before. So here, this is a number, this is a subscript. Okay, and then we divide by delta T. Okay, so we've figured out a number density times a volume to get the total, multiplied by the charge to get the amount of charge. Okay, well, how big is that volume? Well, if this pipe has an area A, a cross-sectional area A, and of the section that we're talking about is of length dx, then our volume, I'm going to group this and this together, our volume is now A, basically length times area. It's a cylinder, length times area, so it's going to be A dx. All of that's divided by dt. All right? Well, that's looking not necessarily the prettiest, but there's something interesting here. What is dx over dt? That's the velocity. NE, A, and the velocity of these charges, however fast they're moving. And that's the drift velocity. I mentioned earlier in an earlier video that as these charges are being pushed through, they reach a terminal speed because of bouncing off the rigid nuclei and the congestion of all the elements in there. They reach a terminal speed and they can't go any faster. And so there's this force, this electric force, Coulomb force, pushing through from an electric field, and this resistance giving them this drift speed. So we give that a sub d, a v sub d. Okay, and so now our question is, well, can we calculate that based on other parameters, right? And we can, if we think about, I'm going to draw a pipe again, and here's some rigid nuclei, and I think about an electron being let's have this electron. The electric field's pointing this way, and this electron's being accelerated by this electric field. Remember, electrons go opposite the direction, so these can move, the nuclei cannot. So it gets accelerated and it hits this, and it recoils off, and then it gets accelerated and hits this, and it recoils off, and gets accelerated and hits the next one, and keeps on going. So its motion is like that, and so that's how it ends up with some kind of average velocity. And that average velocity, we can say, is whatever acceleration it has in between hits. Okay, so there's an acceleration that's this direction, and then there's some amount of time, which we call tau. Okay, tau is the time in between collisions, and it ends up being characteristic of the material. It's based on the density of nuclei and how many valence electrons there are, and so on and so forth. And so this becomes just a property of the material. So silver will have a certain tau, copper will have a certain tau. Okay. Now the acceleration A depends on the electric field by Coulomb's law. But if we have this acceleration for this process and then some average time, then we can find this velocity as an average velocity is just acceleration times the time. So now we can write this NE times E times A times the acceleration A, so lowercase a, times this tau, this time between collisions. Okay, now the number density is a property of the material. The electron is a property of the material, or the charge. The tau is a property of the material. I'm just going to collect those together. Okay, and then times A, and then times its acceleration. Now acceleration, we already know what that is. That's going to be the size of the charge times the electric field. So Q times E. But the charge is an electron, and so we have just E times, little e times big E. Okay? And putting that all together, we have N, E, E. Oh, sorry. I almost made a mistake. The acceleration, let me do this a little bit better. Acceleration is force over mass. I skipped that step. I apologize. It's jumping ahead. And then the force is E over mass. I was going to say, I lost my mass somewhere. Okay. So acceleration by Newton's second law is force over mass. The force by Coulomb's law is the charge times the electric field. Take all that, substitute it in for here, and we get this divided by m. Now the mass of the electron is a property of the material, so we can collect these together. We end up with an Ne E squared tau over m. I'm going to put that all in brackets because those are all material parameters. So if I calculate this number for copper, I'll get a number, and I'll have a different number for silver or for iron or any other conductor. And so I'm left with this A here and this E. Okay. Now, this term, since it's all a property of the material, it becomes really convenient to call it something and just create a table of values for different materials. So we call this the conductivity, and we give it a Greek letter, lowercase sigma. Okay, that's the lowercase sigma. Okay, so we have sigma AE. Now just remember that that is a material parameter, and the text has a table of sigma values. So now you can look it up and see, oh, sigma for copper is some number, sigma for gold is some number. And when you have a problem, you'll see things of that current flowing through gold is such a value, and you're like, oh, I don't have enough information. It's like, oh, well, gold is a number. Gold gives you a number right here, so you can go look that up. Okay, so this is a really convenient way of writing current. One really convenient way is this way, because we can calculate or relate the current to the drift speed. Okay, this is another really convenient way to do it. Now there's one more really convenient way, and that is remembering that what caused this electric field? Well, it was a battery or some potential source. And if the electric field's constant throughout this wire, which it would have to be if the wire doesn't change its widths and everything, then we can say that this equals sigma A, and E is going to be delta V divided by whatever length of that wire. Okay? Because remember that delta V is equal to the electric field times the length if the electric field's constant. Okay, so with that being in place now, I can now group the sigma A over L together times the delta V. I think this delta V, my potential difference. And what's interesting here is that altogether is a property of the object. Not just material. The sigma is a property of the material, but the area and the length are how I shape the material. If I take a copper wire, I can choose a width of the wire, so that gives me a cross-sectional area, and I can cut off a certain length. That would give me my length. So choosing copper means I choose sigma. The diameter of the wire is choosing A, and how much I cut off is choosing L. So all of this is a property of the object I pick. And we like to call that thing 1 over the resistance. So this becomes delta V over the resistance. And so this becomes another one. And in fact, this one is probably the most well-known one in terms of a definition for current. That is called Ohm's law. So Ohm's law states that the current is proportional to the voltage across it and divided by the resistance. This R is called the resistance of the object. And so, being clear, resistance is equal to L over sigma A. And since sigma is conductivity, it's how well the material conducts. And since we're trying to talk about how resistance, how much the object resists flow, we choose another parameter, which is simply 1 over sigma. So it really isn't anything new. It's just, if this is 10, then rho is 1 over 10. Okay? But this now is the resistivity. It's a material property, so silver has a certain resistivity. But now it seems to make more sense. Resistance grows with resistivity and grows with length. More material to go through, and inversely with the area. Okay, so I'm going to go ahead and write this down, or box this in, because that's another definition. We'll use this later in the course. We'll also use this later in the course, in the next reading. But the idea about all this is we were able to apply just certain geometric definitions. And then I like this one where we found VD by looking at some kinematics. We looked at some kinematics here to think about it. We used Newton's second law. We used Coulomb's law, shoved it in there, and then recognized material parameters. Then here we got to use our potential relationship, and then we collected things and ended up with a really simple relationship. I just love that, how this turned out to be such a simple relationship. So we use this a lot. Okay. One last thing before we proceed is there's also another way of thinking about current, instead of just current, but current density, is how much current per unit area is crossing. So if I didn't really care about the width, but how much current per unit area, well, that's just, we define a new thing. Current density is current divided by the area. Okay, and that becomes sometimes convenient. And so if we look at it right here, that's the same thing as sigma E. So we can see how current density is related to electric field.